In late February 1910, Stevens Pass lay beneath snow that had accumulated without interruption for weeks. The Cascade Mountains trapped moisture moving inland from the Pacific, forcing it upward into cold air where it condensed and fell as snow across steep terrain. Douglas fir and western hemlock stood laden with white mass that bent branches downward and muted all sound except wind. Snow fell in shifts, sometimes as fine powder, sometimes as heavy wet flakes that compressed immediately under their own weight. The Great Northern Railway corridor crossed this pass at an elevation near 4,000 feet. The route included switchbacks, wooden snow sheds built over exposed track sections, and the Cascade Tunnel, a 2-mile bore through solid rock. Maintenance crews worked in rotations, clearing track with rotary plows powered by steam locomotives. Telegraph lines connected stations at Scenic, Wellington, and other points along the line. Trains moved through on schedule when conditions allowed, carrying passengers, mail, and freight between Seattle and Spokane. By late February, operations had slowed but not stopped. Snow removal required more hours and more equipment. Plows cut through drifts that reformed within hours. Sheds channeled snow away from rails, but accumulation on their roofs required constant monitoring. Wind redistributed snow across cleared grades, filling cuts faster than crews could work. The railway operated as designed for winter in the Cascades, stretched thin but functional. There was no indication yet that the system would fail. The Cascade Range intercepts storms moving eastward from the Pacific Ocean. Moist air rises along the western slope, cools, and releases precipitation. In winter, this falls as snow. Annual totals in the Stevens Pass area regularly exceeded 400 inches. Slopes were steep, valleys narrow, and avalanches were a known hazard. The Great Northern Railway had built its line through this terrain in the 1890s. Engineers used a combination of tunnels, switchbacks, and protective structures. Snow sheds, long wooden frameworks roofed with heavy timber, covered sections of track where drifting or sliding snow posed the greatest risk. Rotary plows, driven by locomotives, could bore through drifts taller than a rail car. Telegraph systems allowed communication between stations and coordination of train movements. Avalanche forecasting in 1910 was rudimentary. Observers noted snowfall totals, wind direction, and temperature, but lacked formal methods for assessing slope stability. Decisions about train movement relied on experience and visual assessment of conditions. The railway's design reflected an assumption that snow could be managed through clearing and sheltering, not that it could be predicted or prevented. Meteorological records from February 1910 show repeated low-pressure systems moving inland. Snow fell almost continuously. Temperatures fluctuated near freezing, creating layers within the snowpack, some cohesive, others weak. Wind loaded snow onto leeward slopes. The system was designed to handle. By the final week of February, snow had been falling for 9 days with only brief pauses. Accumulation at Wellington exceeded 10 feet. Rotary plows ran continuously, cutting through drifts that refilled behind them. Cleared track disappeared under fresh snow within hours. Wind pushed snow back into cuts faster than crews could advance. Telegraph operators reported similar conditions at every station along the pass. Inside the snow sheds, sound was dampened to near silence. Steam locomotives idled with throttles cracked open to keep boilers warm. Condensation from engine exhaust froze on shed walls and dripped when temperatures rose slightly. Outside, wind moved across the valley in surges, lifting loose snow and driving it horizontally across the grade. Visibility dropped to arm's length during heavy squalls. Measured snowfall for the period exceeded 100 inches. Wind speeds were recorded at sustained levels above 30 miles per hour, with gusts higher. Snow density varied, powder in open areas, dense slabs where wind had compacted it. Clearing efforts focused on maintaining access to the Cascade Tunnel and keeping switches operational, but progress was minimal. Each shift gained a few hundred feet, then lost most of it before the next shift began. The railway did not stop. Trains were held in place, waiting for a break in the weather. Crews worked in rotations, 8 hours clearing, 8 hours resting. Boilers stayed lit. Telegraph lines remained open. The system continued to function, but without forward movement. Duration became the defining factor. Snow fell and there was no relief. 2 passenger trains and a mail train were stopped near Wellington by late February. One westbound passenger train sat on the main line just east of the town. Another, eastbound, was positioned near the western portal of the Cascade tunnel. The mail train occupied a siding. All 3 consisted of multiple wooden rail cars pulled by steam locomotives. Combined, they held over 100 passengers and crew. Operational decisions were made through telegraph communication between Wellington and division headquarters. The standard procedure during heavy snow was to wait for weather to improve, then resume clearing and movement. Trains could not proceed safely through uncleared track or during active snowfall that obscured signals and switches. Backing down the mountain was considered more dangerous than waiting in place. The sheds provided shelter. Provisions were available. The decision was to hold. Inside the cars, darkness came early under the shed roofs. Vibration from wind carried through the wooden structures and into the railcar frames. Stoves burned coal to provide heat. Condensation formed on windows and froze in patterns. Sound was muted except for wind hammering against shed walls and the low hiss of steam from idling locomotives. Switches froze and required manual clearing with shovels and hot water. The grade was too steep for easy movement even in clear conditions. Nothing moved. Days accumulated. Snow continued to fall. The trains remained stationary, engines running, waiting for the weather to break. There was no alternative. The infrastructure was designed to shelter and hold. That is what it did. Above the railway corridor, slopes rose at angles between 30 and 45 degrees. Snow accumulated on these surfaces throughout February. Each storm added layers, sometimes powder, sometimes wet snow, sometimes frozen crust. Wind moving over ridgelines lifted snow from windward slopes and deposited it on leeward ones, building thick slabs in areas sheltered from direct wind. Temperature fluctuations created weak layers within the snowpack where bonds between crystals were poor. Avalanche formation depends on slope angle, snowpack structure, and triggering mechanisms. At Stevens Pass, slopes above Wellington held snow at or beyond the angle of repose for unconsolidated material. Weak layers formed where temperature gradients caused crystal metamorphosis, creating faceted grains that did not bond well with adjacent layers. Heavy snow on top of weak layers created stress. Wind loading added mass asymmetrically. The snowpack above the railway grew deeper throughout the month. No major slides occurred initially. Small sloughs ran down gullies, releasing minor accumulations. Larger masses remained in place, held by friction and the interlocking structure of the snowpack. But each additional snowfall added weight. Each warming period weakened bonds. The slope angle did not change. The load increased. In early March, a brief warming trend raised temperatures above freezing during the day. Snow became heavier, more cohesive on the surface, but weaker at depth. Wind paused, then resumed. The snow rested in place, tons of mass distributed across steep terrain. There was no sound except wind. The mountains held what they had been given, and they held it until they did not. On March 1, 1910, shortly after 1:00 a.m., the snowpack on Windy Mountain released. The failure began at a fracture line roughly 1,000 feet above the railway corridor. Snow separated from the slope along a plane of weakness within the layered pack. Initial motion was slow, a settling, a shift in mass. Then the entire slab accelerated downward. The avalanche moved as a coherent mass initially, then fragmented into blocks and powder. It crossed the slope in seconds, picking up loose snow, uprooted trees, and broken rock. The mass struck the railway corridor with enough force to shear wooden snow shed structures from their foundations. Railcars were lifted, rotated, and pushed off the grade. Steel undercarriages bent. Wooden car bodies splintered. The avalanche continued across the valley floor, carrying debris into the ravine below. The sound was brief, a deep, low-frequency rumble that traveled through the ground and air simultaneously. Then silence returned. Snow settled in new configurations. What had been a railway grade with sheltered trains was now a slope of debris, snow mixed with timber, steel, and earth. The grade itself was gone in places, scraped to bedrock. In other areas, snow buried everything to depths exceeding 40 feet. Survivors from railcars on the periphery of the slide path reported the event lasted less than 2 minutes. Rescue efforts began immediately but were limited by darkness, ongoing snowfall, and the instability of the debris field. Wooden cars had been crushed or buried. Steel components were visible only where they protruded above the snow surface. The avalanche had displaced structures designed to withstand snow loading by orders of magnitude beyond their capacity. Recovery operations began at first light on March 1. Crews from nearby stations and rescue teams brought in by train worked to locate and extract survivors and remains. The ravine below the grade was filled with compacted snow, timber fragments, and sections of rail cars. Probing with poles located bodies and structural debris. Digging proceeded slowly. Snow was unstable, and additional slides remained possible on surrounding slopes. Traffic through Stevens Pass halted entirely. The main line was severed. Mail, passengers, and freight were rerouted or delayed. The railway operated a temporary ferry service across the damaged section while repairs were planned. Wellington, the small community that had grown around the railway station, was abandoned within months. The site was too exposed. The name itself was changed. Later records refer to the location as Ty, after the nearby river. Engineering reviews followed. The railway commissioned studies of avalanche paths, snowpack behavior, and structural adequacy. Within 2 years, construction began on a new tunnel, longer, lower in elevation, and positioned to avoid the most dangerous slopes. The new Cascade tunnel opened in 1929, bypassing the old grade entirely. Snow sheds were improved on remaining sections. Avalanche control measures, including active triggering and slope stabilization, became standard practice. The pass reopened under new operational rules. Trains no longer waited in exposed positions during heavy snow. Forecasting improved. Infrastructure changed. But the mountains did not. Snow still falls in the Cascades each winter, accumulating on slopes that hold it until conditions shift. The railway crosses the range through tunnels now, beneath the surface where avalanches travel. The old grade remains, abandoned, visible in summer when the snow melts and the rails lie rusted in the woods.